Okay, so what are we going to be up to today? Well, we got partway through our work on how we classify discrete time systems into our standard classifications. And so we're going to finish that up today. And particularly, we're going to be working through time invariance and causality. And that'll give us our first grouping, which, along with linearity, become important aspects of our systems if we want to use the analytical techniques that we're going to be discussing over the next few weeks for doing system analysis. So we'll talk about how that connects, how system analysis and the linearity and time invariance connect to that and our requirements for that. And a consequence of that is that we can use a particular response, a unit sample response, as another way to represent the behavior of the system. So we'll talk about what that is, see how we can actually compute it with a few examples using recursion, and then see how we can actually use it to predict whether a system is causal or not, and whether it's stable or not, after we talk about just what we mean by stability in our systems. So that will give us the end of the introduction of discrete time systems and classification, and that'll set us up for beginning our work on time domain methods for doing system analysis next week. So last time we got through, again, some of the basic kinds of classifications of discrete time systems. We determined whether or not our system was recursive or non-recursive, static or dynamic. And we got through linearity, whether a system was linear or nonlinear, as a consequence of the system having additivity and homogeneity and obeying superposition. Those properties are going to be critical for using the analytical methods that we have for solving systems and figuring out what's coming out of systems using analytical methods. The other baseline required property for a system to use these techniques is that it be shift invariant or time invariant. And the way we look at systems in discrete time world for shift invariance or time invariance is very much like it is in continuous time domain. The idea is if we have some input signal, we'll call it x1, and it produces some output signal y. We take that same signal and delay it by a few sample values and put that delayed version through our system. What comes out in that case better look exactly like the original output y1 that's been delayed by exactly the same amount or shifted over by the same amount. So basically we're saying any sample shifts that happen on the input result in an equally sized sample shifts on the outputs. That's shift invariance or time invariance. So shift invariance, if a system has that property, it implies that any sample shift in the input signal produces an equal shift in the output, not any shift, but an equal amount of shifting in the output. It also implies, though, that the basic dynamic behavior of the system is unchanging over time, so that if I put a signal in today or tomorrow or the next day, I get exactly the same shape response out of the system. That is the characteristic of a shift invariant system. And it turns out that while that's a good approximation for most systems in both continuous time and discrete time, in continuous time systems, it's not entirely always true. In analog systems, real world physical systems, things are always degrading, things are always shifting over time, the temperature changing. So in that sense, in a very strict sense, it's difficult to make a continuous time system that's truly shift invariant. Now, over the ranges of times that we care about, they act like they are, and so that's not necessarily a problem. The beautiful thing about discrete time systems, if most of them are based on just computations, and those computations aren't going to change over time unless somebody dabbles with the coefficients or the equations themselves. So it's easier in some ways to make a shift invariant discrete time system than continuous time system. Now, if we're given a difference equation for a system, how do we tell whether it has this property, whether it's shift invariant or time invariant? Well, easier to prove if it's not. There are some clues that we can look for that would tip us off that we actually have a time varying or shift varying differential equation, or difference equation. We can look at the what's ahead of our x and y terms in our difference equation, the things that should be coefficients, AKs and BKs. If they actually end up not being just numeric constants, but some functions of n, well, that is by definition a shift varying or time varying equation, because for each value of n, we're changing basically the coefficients of the difference equation. So that's one that's going to behave differently depending on what index you're starting your new input at. Turns out we also can run into trouble if we have time-scaled inputs or outputs. If we have x of 2n, or if we have compressions or expansion going on, that's a system that's also time varying. Now, shift invariance or time invariance is critically important along with linearity in order to place us in the one kind of system that we can use our system analysis tools on, at least the ones that we'll be learning in this course. And together they make a system LTI, or linear time invariant. An LTI system has those two characteristics, those two classifications. They're linear and they're shift invariant. If they are, then the difference equations that describe their operation have to be of a particular kind. They have to be linear constant coefficient difference equations, meaning in all the y terms and all the x terms, all the leading coefficients in front of them have to be just numeric constants. They can't be functions of n, or they're shift varying. They can't be functions of x or y, or they're nonlinear. And so we would recognize a linear time invariant systems difference equation if all we have are numeric constants in front of all of our x terms and y terms, and we don't have any cross terms like x is multiplied by y's or vice versa. Beyond those, the other property that we're interested in, which was critical in continuous time systems for physically realizable systems, was causality. A causal system is one that can't anticipate. It doesn't need future information in order to operate. So we could say that at any particular time index n sub 0 that we're defining as the present moment, so we're chunking along at that particular instant in time, if we're trying to compute the output for the system at that particular instant in time, it needs to be completely specified by information I already have available to me, inputs that are happening right now or that happened in the past. So the output must be dependent only on present inputs or past inputs, not future inputs. If we need a future input to compute the current output, that's a non-causal system. So we don't want to have future values implied in our difference equation, or else that would be a non-causal system. So what are we looking for? If we assume that we've got our difference equation written so that it's y of n equals some function of inputs and outputs, there can't be any future input terms, y of n plus some tau, like x of n plus 1, x of n plus 5, anything that implies a future input of whose index is further down the road. Turns out also we can't have time compression and expansion terms in our difference equation as well. Like if we have y of n equals x of 3n, well, just take a particular example. At index n equals 3, that equation would say y of 3 requires information on x of 9. Well, at index 3, sample number 9 hasn't come along yet. Going the other way, if we have y of n equals x of n over 2, then if we're looking in the negative index direction, like if n equals minus 4, then computing the value of the output at index n equals minus 4 requires us to know x of minus 2, which again hasn't happened yet at index minus 4. So these compression and expansion terms would apply future information required depending if you're in the positive index or the negative index direction. So here's a couple examples. Let's talk through these, and go ahead and unmute yourself and give me what you think the answer might be. Here's a difference equation. Y of n equals 5x of n plus 1 plus 3x of n minus 1 plus 2. First off, is that a recursive system?
It's not recursive.
Not recursive. Right. We're looking for y of n minus things, previous y output. So it's not recursive. How about linearity? Is it linear? There's no x squareds or y squared or x times y, so that's fine. There's a plus 2 here. That's actually going to make it nonlinear. It is shift invariant. There's no functions of n. It's a dynamic equation because we have previous and future values needed to compute the current output. So that makes it dynamic, not static. The fact that we need a future input makes it non-causal. So this is a non-recursive, non-linear, shift invariant, dynamic, non-causal system. Here's another one. Y of n equals 3x of 2n minus y of n minus 2. Now we have a recursive term here. So this one's definitely recursive. It's linear. There's no constant. There's no squares, cubics. We have a time compression term in here, so that's a problem. It's making it shift variant. And again, this is making it recursive. It's a dynamic system. I need to remember y of n minus 2. And this 2n is also messing up causality here. Here's one that's easy to recognize as a nonlinear system because we have a squared term in there. It's recursive because our y of n minus 1. So recursive, nonlinear. Nothing to mess up shift invariance, so that's okay. It's got a delay on the y side, making it dynamic. And actually, this is a causal system. So just the linearity is messed up and it is recursive. Okay, so get the hang of this. This is a skill that we want to have. We want to be able to look at a difference equation and particularly make sure that we know whether it's linear or not and shift invariant or not so that we can tell if it's in that class of LTI systems. Most of the ones we're going to deal with are dynamic because static ones are pretty boring. Most of them will be causal, although they don't have to be if you're doing it computationally, as long as you can tolerate some delay, some sample delays between your computed output that you want and when the data is coming in. And recursive or non-recursive is actually going to be a design decision we'll make when we get to designing discrete time systems, whether we want to do an implementation that's recursive or non-recursive. Okay, so again, together, linearity and shift invariance, those were two keys. They give rise to our having an LTI system. And if we do, a nice characteristic of that is that beyond the difference equation, there's another function that we can use to describe the dynamic behavior of the system that gives us all the information we need to know in order to do system analysis, in order to predict what's the output going to be for a given input. As long as the system is relaxed, that means we have zero initial conditions, which in the case of a discrete time system means the output, before we apply a new input, the output has to be 0. So it's settled down. If there were any previous inputs, those have all worked themselves out of the system so that the whole response of the system now is totally because we put a new input to it. And we can predict what that response is going to be using this single unchanging response function. And it's not changing because we have a time invariant system. That function we'll call h of n. And that h of n function happens to be the output of the discrete time system when the input is a single unit sample sequence, a delta sub n sequence. That was that single magnitude 1 sample value that happens just at n equals 0 and nowhere else. So if I put a unit sample sequence, which look like this, again, it's 0 everywhere except n equals 0, we have 1, 1. I put that into the system, whatever comes out is what I call h of n, the unit sample response. Very clever name for a response to a unit sample sequence. And you'll recognize this same kind of workup to this and the nomenclature as well. H of n is like h of t was in the continuous time domain, whereas there we called it an impulse response. Here we call it a unit sample response. In fact, some textbooks and some folks also use that same terminology for discrete time systems. They call this an impulse sequence, and this the the discrete impulse response. But technically, it's not. Technically, this is a unit sample sequence, and we're getting a unit sample response. Although functionally, it is the same idea as the impulse and the impulse response to a continuous time system, because that, despite the fact that an impulse is this scary thing that's infinitely tall and infinitely narrow and hard to then reconcile what that could possibly mean, in reality, it is effectively a great big one. It's the weight of that impulse that matters. It has an area of one. So when we put an impulse into the system, it's like putting a great big one in. Well, here in discrete time, we're literally going to do that. We're going to put in 1, 1 at n equals 0 and see what the system does. And with this response, then we can use that information to predict what the system's going to do for any input sequence. Because you give me any input sequence, and I can recreate that with a sum of scaled and shifted unit sample sequences. And you were doing that for homework 1. So if we have a sequence that looks like this, it's 0 up until n equals 0, and then it has 3 samples, A, B, and it goes back to 0. I can describe that input signal as the sum of 3 other sequences, all that are unit sample sequences, just scaled versions, multiplied versions, and shifted versions of a unit sample sequence. We'll take an A times a delta sub n sequence to give me an A value at n equals 0. We'll add to it an A times delta sub n minus 1 unit sample sequence, a shifted and scaled one, to get this one sample at n equals 1 of the value A. And then take a unit sample sequence, shift it over by 2, and multiply it by B to produce the one sample here at n equals 2 in my final sequence. So we can take any arbitrary input sequence and describe it as a long collection of summation of scaled and shifted unit sample sequences. And you were doing that for homework and creating this summation formulation that we had for a way of describing the sample values in an input sequence. Well, if we have that way of breaking up our discrete time input signals into these individual sequences, and we know what this system's going to do when we put one of these in that's unscaled. If we put a delta sub n in, we get h of n out. We can predict what the system's going to do for any input by just scaling and shifting our unit sample response. So if delta sub n produces h of n, then a times delta sub n produces a times h of n. And if a times delta sub n minus 1 goes in, we get an a times h of n minus 1. So scaled by the same amount, because the system is linear and homogeneous, shifted by the same amount because it's time invariant. So if we have a linear time invariant system, we can use this prediction method. We just break up the input into a bunch of scaled and shifted unit sample sequences, and the output is nothing more than a equally scaled, equally shifted collection of unit sample responses. And so that's kind of like breaking up the input so that we can use superposition, which is a characteristic of linear systems, and time invariance to create a simple way to compute the output kind of sample by sample and just adding up all the residual results. And it turns out this summation methodology is a perfectly valid way to do it, and a whole technique we're going to learn to use for doing system analysis. And you'll recognize this as the idea behind convolution. Except this is the discrete version of convolution, where instead of nasty integrals, we have simple sums. But the concepts are all the same. And it's based on this idea. We're actually just applying superposition and time invariance to break up the input into something we know the response to, so we can just scale and shift and add up the results in order to predict the output for any given input. Now, before we go into the actual methodology of convolution, we're going to park that for a week or so, but just introducing the concept here to show that, well, two things. It's because we have linear time invariant systems that's going to make that possible. So it's important for us to recognize whether our system is or is not linear and time invariant. But it also introduces us to this new way of describing a system, the unit sample response, H of n. And we want to look at now, how would I determine what the unit sample response is for a system? And what else can that tell me about what classification my system falls into? I can't really have a unit sample response that I use for this generalized convolution method unless I have a linear time invariant system. But can I learn other things about my system, like whether or not it's causal or not, or whether or not it's stable or not from my unit sample response? And that's what we're going to do next. But H of n then we can think of as equal to the difference equation in that it contains all the information I need to know to compute what the output's going to be for a given input, as long as the system starts off relaxed, as long as the output is 0 at the time that we hit it with a new input. Now, how do we find this? Well, right now we only have one way to do system analysis, to find the output of the system for a given input. That's through recursion. And in order to do that, we will literally apply the definition of what a unit sample response is. The unit sample response is the output of the system. It's whatever comes out when my input is the particular input of a unit sample sequence, a delta sub n sequence. So I'm going to put in 1, 1 at n equals 0 into my system, and whatever comes out, I call H of n. And we can do that numerically using our recursion table. So the unit sample response, H of n, is the Y of n, the output, when X of n is a unit sample sequence. Let's keep that definition in mind. Okay, so let's do that. Let's use a recursion to find the unit sample values, unit sample sequence values. And again, recursion can only give me sample values. It can't give me a closed form or analytical expression necessarily for that function, but it can give me the sample values. And let's try first a non-recursive system. So here's one we've got, it's non-recursive, there's no Y feedback going on, it's all feed forward. And we might recognize from this difference equation that from this block diagram that the difference equation is going to be Y of n equals 5x sub n plus 3x sub n minus 1 minus 2x sub n minus 2. And this is a linear, time invariant, dynamic, causal difference equation. So let's see if we can find a unit sample sequence for this. And we'll need a recursion table to do that. So if we have 3 terms in our difference equation, we have an x sub n minus 1, x sub n minus 2. So we'll need columns for each of those. We'll need a column to compute our output for those. We'll put up our difference equation in here for the computation. We'll start just before n equals 0 when we start our unit sample sequence. And so just so we see what's where, you don't need to write these indices into your tables. That'll take quite a while, but just to remind us that here x sub n at index 0, that's our x sub 0 term, and so on. So just to give me some locators here. In the first column, in the x sub n column, we'll put in the values of a unit sample sequence. Well, unit sample sequence is 0 everywhere, except at n equals 0, it has a single 1 value. So that's pretty easy. So 0, 1, and all zeros after that. And go ahead and fill that in your table. X sub n minus 1 should look like exactly that same column, but everything is shifted down one row. It's delayed by 1 sample time. So we'll take this unit sample here in 1 at x of 0, or at index n equals 0, and move it down here to n equals 1, and have 0 everywhere else. Likewise, x sub n minus 2 is the same sequence, except the 1 now is down 1 more position, down at index n equals 2. And since I don't have any feedback terms, any recursion terms, this is actually a simpler recursion to operate, we have all the information we need to now go row by row and compute the output for a given input. Here, my difference equation, that should say x sub n minus 2 over here. So you need to fix that in your notes. First, in the first row, we put 5 times 0 plus 3 times 0 minus 2 times 0 gives us 0, and that's kind of our initial condition to get going. In the first row at n equals 0, we take 5 times this column, so 5 times 1 plus 3 times 0 minus 2 times 0 gives us 5. Then the next row, we have 5 times 0 plus 1 times 3 plus 2 times minus 2. And that gives us just the 3. And then we have 5 times 0 plus 3 times 0 plus 1, or 1 times minus 2, giving us minus 2. And then after that, we don't have anything other than 0 contributors. So all the rest of those outputs for our unit sample sequence are going to be 0. Okay, so here is, if we put in a unit sample to our x sub n, starting at n equals 0, what comes out is 5, 3, minus 2, and then 0 after that. So here's what came out. And it turns out there's some important things to notice here. First, if we look, we only got 3 samples that weren't 0 out of this system. And that's the characteristic of a non-recursive system. A non-recursive system will always have a unit sample sequence that has a finite length, a finite number of non-zero values. In this case, I have 3 of them. Here's my n equals 0, n equals 1, n equals 2, and then I'm back to 0. That's what a non-recursive system is always going to do. And if we look at the original difference equation for this system and apply the definition of a unit sample response, that was y of n equals, or h of n equals y of n when x sub n equals delta sub n, then everywhere in this equation that there's a y, I can put h. Everywhere there's an x, I can put a delta. So we have the definition of the unit sample sequence. H of n is 5 delta sub n plus 3 delta sub n minus 1 minus 2 delta sub n minus 2, which is exactly what we're seeing here in the sequence values. The 5 delta sub n, 3 delta sub n minus 1, minus 2 delta sub n minus 2, and nothing after that. We call these kind of systems FIR, finite impulse response systems, because they have a finite length unit sample response. And so FIR, discrete time systems, have this characteristic. All non-recursive systems are FIR, finite impulse response. So if you have a non-recursive system, you're guaranteed that the unit sample response will have a finite length. Now, you probably also notice something else interesting. The actual values of the unit sample sequence that came out, 5, 3, minus 2, exactly matched the coefficients in the difference equation, the B coefficients. We got out B0, B1, B2, because we had that traveling 1 going through the recursion table. Each time it picked up one of these coefficients at a time and made it part of the output. And that is also the characteristic of a non-recursive system. The unit sample sequence is always the same as the values of the unit sample sequence are always the same as the B coefficients in the difference equation. Now, there aren't any A coefficients. There's only the A0 coefficient that goes with the y of n term, and we're always normalizing that to be 1. And so we only have B coefficients, and those will exactly match the sample values of the unit sample sequence if you have a non-recursive system. So we say the H of Ks are the same as the B Ks. Now let's try that for a system that has a feedback. Let's try a recursion table on a recursive system and try to find its unit sample sequence as well, its unit sample response. So here's a fairly simple recursive system. I have two feed-forward paths, but I do have one feedback path here where I bring y of n around to make y of n minus 1. I'm going to multiply it by 1/2 before I bring it back in. So the difference equation here is 1 times x of n. Here's my x of n minus 1 multiplied by 1. And I'm going to subtract off 1/2 of y of n minus 1. So definitely recursive. It's still linear. It's still shift invariant. It's still causal. It's still dynamic. Now let's have a look at what its unit sample sequence looks like. And we'll pull up another recursion table for that. This one's kind of like the first one we worked out on Wednesday. Again, our difference equations up here for computing y, I need an x sub n column, I need an x sub n minus 1 column, and now I need a y of n minus 1 column that's going to take the y of n values and shift them down by 1 position after I compute each of them. The setup is still the same, and again, you don't have to put in all these indices. We put in our unit sample sequence for x sub n, 1, 1 at n equals 0, and 0 everywhere else for that column. X sub n minus 1 looks just like in the previous time. We'll take the 1 and shift it down to n equals 1 and put zeros everywhere else. Now I do truly need somebody to tell me an initial condition. They need to tell me for sure that the system was relaxed, had to be 0 at all times prior to n equals 0. So let's make that our assumption. And that it was prior to that even. Now we can go ahead and compute what's going to happen starting at n equals 0 and moving forward. We take the y of minus 1 and bring that forward as the y of n minus 1 term at n equals 0 and apply our difference equation to this row of data. We have 1 times x of n plus 0 times x of n minus 1 minus 1/2 times 0, giving us just 1. Let me take that 1, copy it down to be y of n minus 1 in the next index. And then same thing, process the difference equation, take 1 times x of n, add 1 times x of n minus 1, subtract 1/2 of y of n minus 1, and in this case get 1/2. And if you keep going through that, we've got to carry that 1/2 down to the next place, run through that difference equation. Now we notice that the two terms from the x side, x of n minus 1 and x of n minus 0, are only going to have zeros from now on. So the only thing I have to worry about in my difference equation is this y of n minus 1 term. And I'll keep multiplying it by minus 1/2, bringing it over, multiply it by another minus 1/2, bring it over, and so on. So it's oscillating back and forth, positive, negative, and the denominator is doubling every time we go to another column. And that's going to continue indefinitely. So an important thing that we're seeing here is, well, number one, the output's oscillating, but that's okay. It's decaying, that's probably good, but it's never ever going to get exactly to 0. It's just going to keep getting closer and closer and closer and closer as it wobbles back and forth above and below the axis. Next time it's going to be 1/28th, and then minus 2/56, and then plus 1/512th, and so on and so on and so on. It's going to get infinitesimally close to 0, but never quite get there. And so when we put in 1, 1, we got a kind of an oscillating response. It looks like it died out to 0, but if we blew up the axes here and zoomed in on this, we would see it's continuing to bounce back and forth, getting closer and closer and closer, but never quite getting to 0. So our recursive system now has a very different kind of unit sample response. It has one that's going to go on forever. It's never going to quite settle out to zero. It might be converging, it might be getting smaller, which is probably good, but it's never going to get there. These kind of systems that have this sort of unit sample response we call IIR, infinite impulse response systems. FIR and IIR, finite impulse response, and these are infinite impulse response. Literally, the impulse response or unit sample response is infinitely long. Now, that doesn't inherently make them unstable. It's just that that's their characteristic. Once they're hit with any kind of input, they never quite settle out again. Now, this is where one place where, different from the FIR filters, where I have a very simple way to analytically get to my unit sample response. I just replace y of n with h of n and replace x of n with delta sub n. If I try to do that with a recursive difference equation, I get a description of the unit sample sequence that's dependent on itself. I have a recursive equation that I can't solve directly. And I can convert this to be to describe h of n minus 1 and plug that in here, but then I have h of n in terms of h of n minus 2, and I can do that indefinitely, but never quite get a complete answer. So I can't do with this what I did with the FIR systems. Turns out if you stared at this sequence long enough, you might be able to invent an analytical or equation type description for this signal. One of them might be, for example, delta sub n to get the 1, and then a minus 1 to the n minus 1 to get the sign to flip back and forth. And this decay by a factor of 2 in the denominator every term would be like a 1/2 to the n. But I can't start that right away. I've got to start that afterwards here. So there are several different ways to describe this sequence, but you can come up with an analytical expression, a function of n, that describes this sequence of values. Even though it's an infinitely long sequence of values, we can determine all of its sample values from this form. Now, how I get from the difference equation to this expression, this analytical expression for h of n, is going to require us about a week's worth of mathematics to learn. That's next week. For now, let's just acknowledge that there is a way, even though this is an infinitely long unit sample sequence, I can actually write an analytical expression to give me all these values. I just can't easily get it directly from a simple substitution like I can with the FIR filters. Okay, a few things I can learn from this unit sample sequence. First of all, I can tell if a system is causal or not by looking at its difference equation or by looking at its unit sample response. If I'm looking at the unit sample response, I'm looking for the characteristic that all the sample values of the unit sample response have to be 0 for all indices less than 0, for all negative time indices. That's because my h of n is the response to a single 1 at n equals 0. And so I'm not expecting it to respond before I hit it. If it has any response values for indices prior to n equals 0, that means it responded before I gave it an input. That's definitely a non-causal system. So I can tell causality either from the difference equation or from the unit sample response. I can also tell if a system is stable or not from either the difference equation or from the unit sample response. And it turns out it's easier in some senses to determine if it's stable from the unit sample response if I have that available. Now, we haven't really talked about what we mean by a stable system. We're going to start with a very simple-minded definition of a stable system. Basically, our definition of stability is a system is stable if there is absolutely no finite input signal that I can apply to it to make my system run away to infinity. So there doesn't exist any input sequences that's going to make my output keep increasing on forever. never turn around and get back heading towards zero. We call that kind of definition of stability bounded input, bounded output stability, BIBO stability, which just means we're saying if I put in a bounded input, any bounded input sequence, and by bounded input, we mean all of the sample values of x sub n for all n, their absolute values have to be less than some upper boundary. That upper boundary can be 87 million, but as long as they're all contained within an upper bounds, that's a bounded system. And the idea of bounded input, bounded output stability is I'm going to call a system BIBO stable if for every input sequence that follows, that obeys this bounded definition, the system has to respond with a bounded output. It has to likewise have all of the absolute value of all of its sample values less than some finite boundary. Now, this boundary M2 on our output doesn't have to be smaller than the input one. It could be bigger, but as long as it's bounded, as long as there is a finite level that's a boundary for all the output sample values or their absolute values, then we consider the system stable. So it can create some really, really huge values, but as long as it turns around again and doesn't exceed that limit, then it's a bounded input, bounded output stable system. Okay, now how do I tell whether a system meets this requirement? Well, the bad part about this very simple, straightforward definition of stability is if I want to prove a system is stable, I would literally have to try every possible input sequence to make sure I didn't generate an unbounded output. It's easier to, again, show that a system is unstable by finding any one input that makes it take off to infinity. If I can find any one as soon as I find one, I rule out the system is not stable. But if I can't find one of those, I can't be sure that the system is BIBO stable until I've tested every possible input. So we need some other criterion. Well, that's where the unit sample response comes in. A system is stable if its unit sample response follows this paradigm. If I take the unit sample response and all of its sample values, take their absolute values, sum them up over all k, and get a finite number out of that, then the system is stable. And we recognize this expression as saying the unit sample response, h of n or h of k, must be absolutely summable, meaning the sum of its absolute value has to be within some finite bound. And as long as that's true, then it turns out the system is stable. Now, it turns out those FIR filters that we get a finite number of finite values out of them that match the difference equation coefficients, they're always absolutely summable. There's no way that they can not be absolutely summable. And so a wonderful attribute of FIR systems, non-recursive systems, is they are always stable. Always, 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 underline, exclamation mark, always stable. And so when we're designing systems, if we have a choice, if it's critical that the system be absolutely stable, we can always design them using an FIR style discrete time system. Now, there may be other reasons why we might prefer not to do that, when we might prefer an IIR system, but this is one wonderful attribute of FIR systems. So here was our original example we did. Our FIR filter had this unit sample response. We sum up all the terms. They're all, take the absolute value of all of them. We get 5 plus 3 plus 2, because we're taking the absolute value, get a finite sum of 10. There's no way that that finite number of samples is going to go to infinity. So for sure, we passed the absolutely summable test. What about our recursive filter? We said it was an infinite impulse response. And so the question is this expression here that describes all of the sample values, can I sum the absolute value of this? And well, okay, let's do that. The delta sub n is going to give me a 1. We're taking absolute values, so the minus 1 is gone now. We don't want any negative signs. And I'm left with 1/2 to the n, starting at n equals 1. So I have a summation of that, but 1 happens to be the same 1/2 to the n when I let k or n equal to 0. Then it should have my same indices, k, and this should be either n down here or k up here. They need to be the same. So that's equivalent to the sum from k equals 0 to infinity of 1/2 to the k, which, if you remember your sequence sums, as long as this value is less than 1, it's 1 over 1 minus that value, which in this case gives me 2, which is a finite number. And so even though we saw this unit sample sequence bouncing back and forth, it was converging towards 0, and it does have a finite absolute sum, and so that's actually a stable system. So again, these properties of linearity and shift invariance are really foundational for us to use these methods for analyzing discrete time systems. It's going to be the basis on which we use superposition and time invariance to do convolution. A lot of our methods are similar to convolution in that they predict the system response to some arbitrary input signal by describing that input signal as a sum of weighted and shifted simple functions, where I've chosen my simple function to be one that I either know intuitively or can find easily the response of the system to just that simple function, so that computing the output becomes just a matter of adding up a bunch of scaled and shifted copies of those simple function responses. And our methods will just change what the simple function is, right? When we're doing convolution, we'll be using unit sample responses. When we're looking at frequency responses, we're looking at breaking things up into sinusoidal kinds of signals. When we're looking at Z transforms, we'll be looking at complex exponential responses. But again, all of these rely on us having linear time invariant or linear shift invariant discrete time systems in order to apply these methods. And so far, we've got one method for doing system analysis. That's recursion, a table method for finding the output for a given input and a given set of initial conditions. Next week, we're going to start working on doing that same job with analytical functions, with functions of n to describe my input signal, with a difference equation to describe my system, and to come up with a function of n that describes my output signal. And then we'll finish off by our last time domain method the following week or so, which will be coming back to convolution and using the unit sample response of the system. And how do we first use this method number 2, solving difference equations, to determine the analytical form of the unit sample response h of n, and then how do we use that in a convolution sum, not a convolution integral, a convolution sum, to determine the output of the system of a relaxed system for a given input signal.